So let's talk about quantum computers. You've definitely heard the buzz, right? That they're right on the edge of changing, well, everything. But how much of that is real right now and how much is just hype? Well, a fascinating recent paper put that exact promise under the microscope. And trust me, what they found is going to make you think. I mean, that's the dream, isn't it? Solving the unsolvables? We're talking about designing new medicines in days instead of decades, creating financial models that are basically uncrackable. The potential is just massive. And we keep seeing these headlines, one after another, claiming some new quantum speed record has been shattered. But are we really at the finish line? Or are we even running the right race to begin with? So here's how we're going to break it all down, following this scientific investigation. First, we'll get into the hype. Then we'll ask the most important question: what does runtime actually mean? From there, we'll dive into 3 huge claims of quantum advantage, see if they were even racing a fair competitor. And finally, I'll leave you with a simple guide for spotting the real breakthroughs from all the noise. Okay, so at the heart of all this excitement is this one core idea: quantum advantage. It's that magical tipping point, the moment a quantum computer solves a problem that is, for all practical purposes, impossible for any classical computer on Earth. You can think of it as the starting pistol for a whole new age of computing. And that right there brings us to the absolute core of this whole investigation. If this is a race between quantum and classical, how are we timing it? Because it turns out, the way you hold the stopwatch, it changes absolutely everything. The researchers behind this paper, they argue that a lot of these big claims of quantum speedups are frankly misleading. Why? Because they're only timing the flashy, glamorous part of the race while totally ignoring all the boring, time-sucking steps that happen before and after. Instead, they say we need to measure something called end-to-end runtime. And it's actually really simple. It's the real time on the clock from the second you hit go to the moment a usable answer actually pops out. It has to include everything: the good, the bad, and yeah, the surprisingly slow parts. Think of it like baking a cake. Some reports only measure the computation time, the time the cake is actually in the oven. But the true end-to-end runtime, that includes prepping the ingredients, mixing the batter, waiting for the cake to cool, and even doing the dishes. For quantum computers, these extra steps, like programming the thing, reading out the answer, and letting the system cool down again, can take up almost all the time. Okay, so theory is one thing, but let's see what happens when we actually apply this super strict end-to-end timing to the real world. We're about to put 3 recent, really high-profile claims of quantum advantage right under the microscope. First up, a method called quantum annealing. It's a special kind of quantum computing built to solve tricky optimization problems. Like finding the absolute most efficient route for a delivery fleet or the perfect shape for a new drug molecule. A huge study claimed a massive advantage for a quantum annealer from D-Wave. All right, look closely at this graph because it tells the entire story. See that orange line way down at the bottom? That's the original claim. It's only measuring the baking time, the annealing. And yeah, it looks like a huge win for quantum. But now, look at the red and green lines up top. That's the real end-to-end time. The second you include all that overhead, the advantage just evaporates. The speedup is gone. Poof. So what on earth happened? Well, the main culprit was the readout time. Getting an answer means you have to measure this incredibly fragile quantum state, and that is a slow, difficult process. In this case, the actual quantum computation part took between 0.5 and 27 times microseconds, but just reading the answer, that took about 200 microseconds. The cleanup took almost 100 times longer than the baking. Okay, on to our second case study. This one involves something called Simon's problem. Now, you don't need to be a physicist to get this. All you need to know is that it's a problem specifically designed to show off how great quantum computers are. In theory, a quantum computer should be exponentially faster, needing way fewer steps to get to the solution. But here's the crucial catch. Needing fewer steps does not automatically mean less time. It's like this. Imagine the quantum computer is a brilliant detective who can solve a crime by asking just 3 perfect, insightful questions. The classical computer is more of a brute force detective who just asks a million random questions. Now, the quantum detective is obviously smarter, right? But what if each of its perfect questions takes an entire hour to set up and ask, while the other detective can just fire off its million questions in 5 seconds flat? Who's going to solve the case first? So what was the actual result? For the problem sizes they tested, a good classical algorithm running on a normal GPU found the answer in 35 milliseconds. The quantum computer? It was estimated to take around 2 times 10 seconds. That's not an advantage. The classical computer was nearly 100 times faster. And this brings us to the last and maybe the most important piece of this entire puzzle. It's not enough to time the race correctly. You also have to make sure you're racing against a world-class competitor. This quote from the paper just says it all. It is super easy to win a race if your opponent is, not very good. And it turns out a lot of these quantum advantage claims come from comparing a brand new quantum algorithm to a classical one that's old, outdated, or sometimes just the wrong tool for the job. And that is precisely what the paper found in its third and final case study. A hybrid algorithm claimed a huge speedup on another optimization problem. And sure, it was faster than some standard, off-the-shelf classical methods, but the moment the researchers put it up against a state-of-the-art classical algorithm designed to run on modern GPUs, the quantum advantage disappeared. They weren't just timing the race wrong, they were racing against the wrong opponent. So after all that, where does this leave us? Well, the point of this whole analysis isn't to be a downer or to poke holes in headlines just for fun. It's to give all of us a toolkit, a clear set of rules for a fair race, so we can become much smarter consumers of quantum news. The paper's conclusion is, it's direct and it's unambiguous. When you use proper end-to-end timing, and when you compare against the very best classical algorithms we have, a true practical runtime advantage has not yet been shown on today's quantum hardware, period. So the next time you see a big headline screaming about quantum advantage, here's your checklist. Ask yourself, did they measure the total wall clock end-to-end time? Did they account for all the overhead, the boring stuff like data transfer and readout? And maybe the most important question of all, did they compare it against the absolute best, most modern classical algorithm for that specific problem? If the answer isn't a clear yes to all of those, you have every right to be skeptical. Look, this does not mean the quantum dream is dead. Not at all. Far from it. This technology is moving forward at a dizzying pace. But what this investigation does is give us the tools to be critical thinkers, to separate the genuine breakthroughs from the hype. The race is very, very much still on. But now, we all know exactly where to watch for the finish line.